This video is about the greenhouse effect. It is the fifth video on Topic 8, Energy Production of IB Physics. This topic is part of the core materials, so it's the same for SL and HL. Take a moment and read the success criteria that we will cover in this video. Pause the video if necessary. Okay, let's first talk about albedo. This is similar to the emissivity value discussed in the last video, but this is dealing with the amount of reflection from radiation landing on a body. Again, there's no units because it's just a ratio. And one of the key words here is scattered. We have the albedo is the total scattered power over the total incident power. Make sure to use that word when you're describing this effect. Now, there are many different factors that will affect the value of albedo. Hopefully you can conjecture that white houses in the Mediterranean will also have a high albedo value. They will scatter the radiation hitting it, absorbing less, allowing the houses to stay cooler. Here are a few other examples. Okay, moving on to the greenhouse effect. Let's start with the effect of the atmosphere. So some of the radiation from the sun will be reflected naturally, and the remainder will continue on to the Earth's surface. That's what we're seeing here. It will be absorbed and re-emitted. Typically as infrared radiation. That's what we're showing right here in the picture. If the Earth was a black body, all the incident radiation would be emitted. On the way back out through the atmosphere, some of this infrared radiation may be absorbed by the gases. When it's re-radiated, now we're looking in this area, some of it will be radiated in all directions, not just away from the Earth. So that means some of it will be directed back towards the Earth, causing it to get more infrared radiation than there was if there was no atmosphere. This will cause additional heating of the Earth. So some people call what's happening right now an enhanced greenhouse effect, because the Earth really is warmer because of our atmosphere than if it didn't have it. Gases that would be capable of absorbing that infrared radiation and re-radiating it back to Earth are methane, water, carbon dioxide, and nitrous oxides. By increasing the concentration of these gases, we're changing that equilibrium that had been established. A new equilibrium will be established with equal energy coming in and being given off. And in turn, this will be at a higher temperature than before, thus enhancing the effect of our atmosphere. So, what makes a greenhouse gas? So, we need it to be able to vibrate close to that frequency of the infrared radiation. You can take a look at the other points I have on my slide. You should know examples of natural sources and anthropogenic sources. Yes, anthropogenic, because it's not really man-made. Women and children had a hand in this as well. Anthropogenic just means created by humans. So let's look at an example of why we might use this energy coming into the Earth and giving it off and come up with a temperature that would be needed for equilibrium. So let's first calculate the intensity of the sun's radiation on the Earth. Now, the solar power is going to be incident on the Earth, and if you think about it, it's going to be hitting a circle, right? If you put a ball in front of a shining light, the shadow that's created will be a circle. But since the Earth is rotating, that will be spread over top of the entire sphere. So the total power received by the Earth from the sun would be the solar constant times the area of the circle it hits, divided by the total surface area of the Earth. In other words, at any moment of the day or night anywhere on the Earth, 1 square meter of the surface might be thought to receive 340 joules of energy every second. But remember, I started this video talking about albedo, and that's because the Earth will have an average albedo of about 0.3. So of that 340, about 107 watts per meter squared is actually going to be reflected back before it ever gets to the surface. That means if we have an equilibrium, 233 watts per meter must be radiated. Okay, so we now have this power that has to be radiated. Let's use the Stefan-Boltzmann law that we did in the last video. We can calculate that temperature we must have in order for us to be radiating 233 watts. And since the Earth is not a black body, we're going to have an average emissivity value of about 0.6. Okay, so let's start with the Stefan-Boltzmann law here. Power equals emissivity times the Stefan-Boltzmann constant times the area and temperature to the power 4. Don't forget, this will give us temperature in Kelvin. Well, I don't have the power, I have the intensity. So I'm going to have to take my intensity value, multiply it by the area. I'll just leave A for now. And if I put all the other values in, I can see that the area is going to cancel out on each side. Okay, so now if I rearrange this formula for T, calculating that in, I will get, which is about 14.7 degrees Celsius. Looking online, most places say the average Earth temperature is around 14 degrees Celsius, so we're pretty close. This brings up a point we should mention. Remember, we have something called the nature of science. One of the things we want to think about is why we do modeling, because we're trying to understand what's actually happening. So whenever we talk about climate change or predictions of, what it's going to look like in the future, we have to take both simple and complex modeling to try and see if we can more or less predict into the future. Some reasons we might use a simple model like we just did earlier is sometimes things are so complex, if we didn't start by making some assumptions, we'd never get to an answer. But then as we get more and more advanced and we understand places more and more, for example, this question I introduced the albedo and the emissivity. We can then perhaps get closer and closer to the answer we're looking for. Things to think about when we have the nature of science question, which will be somewhere on the paper 1 and paper 2. Please make sure you review the different parts of the nature of science. As for the example we just went through, here's some of the limitations of the model we used. We said the planet was basically as a whole. We came up with an average intensity, an average power emission, but that's not really going to be the case. We also don't have anything like feedback loops. For example, as soon as we increase the temperature, we're going to then melt some of the polar ice caps, but that means we're going to decrease the amount that's reflected, decrease its albedo, which then will have an additional effect on our values. So here are the success criteria one more time. I hope now that you've seen this video, you can meet these success criteria.